We've come to the final video in this module on combinatorics. We've seen a lot of different ways to formulate and solve counting problems and introduced several tools for solving them. As you are surely aware by now, these problems can be very tricky. Solutions that seem perfectly logical might contain hidden assumptions or incorrect interpretations that might lead to a solution that overcounts or undercounts or just isn't even the correct approach in the first place. In this video, we're not going to introduce any new concepts or tools, but instead review some problem-solving concepts that will help you stay on the right track when working a combinatorics problem or any other kind of problem. The first concept to keep in mind is try to understand the problem first before using math. Don't begin by applying formulas. Instead, begin by using your human brain to comprehend what exactly is being done. What are the data in the problem? What are the conditions on the problem? What are we counting? A powerful way to understand a problem is to look at it in different ways. For example, can you draw a picture or a diagram that represents the problem? Can you physically act out the situation to understand how the process you are counting actually unfolds? It's hard to apply the right math in the right ways until we have come to terms with the problem first by carefully reading and understanding it. The second concept is to compare the problem you have to problems you have seen before. For example, is the situation you are counting like the license plate problem? Or is it a distribution style problem that would involve stars and bars? If so, then how is it like those? Can you explain the way that the problem you have relates to a problem you have seen before? Then once you've compared, you can ask whether the solution to the other problem might lead you to a solution to the new problem. The third concept is related to the second one. Generate lots of examples and data and try to solve the problem in a specific related special case or solve a simplified version of the problem first. As we've seen many times already, specific examples do not belong in a general solution to a problem, but it's often nearly impossible to truly understand a new problem without doing reconnaissance work first by looking at specific examples or simplified versions of the problem. If you can work the problem in special cases, look at all those special cases and see what they have in common. You can also use a computer at times to actually enumerate and count the situation you are counting by having the computer generate a lot of examples for you very quickly, and then you can use your human brain to reality check your own solution. Fourth, and finally, to repeat something just said, reality check your solution. Does the answer make sense? For example, look at the problem of counting the number of 8-bit strings that begin with either a 1-0 or that end in a 1-1. If you solved this problem and came up with an answer of, say, 512, you should reality check this and realize that it's not even possible because the number of 8-bit strings without any restrictions at all is 2 to the 8th, which is 256. The bit strings being counted are a subset of all those 8-bit strings, so the answer to your problem cannot possibly be larger than 256. Particularly in counting problems, an important reality check we always need to perform is asking ourselves if the method we used to count the situation could have possibly overcounted, that is, counting identical arrangements as being different. We've seen this principle at work already, for example, when differentiating between forming subsets of a set versus forming ordered lists from a set. Overcounting is a constant debugging issue in counting problems, and we have to stand guard against it. Let's look at a real problem and see if we can crack it with our human brains first, and then apply the right math to it once we understand the problem. Let's suppose I have a class with 12 students and I want to put them in 4 groups of 3 students each for classwork. How many ways are there to do this? You may be tempted to start pulling out formulas and doing things like computing 12 choose 4 or 12 choose 3 or something of that nature, but it's too early. I haven't really understood the problem yet, so the first thing I'm going to do is play with some examples. Here are 12 students, and I'm just going to try to understand what's happening first. So one way to create the groups is to have students 1 through 3, 4 through 6, 7 through 9, and 10 through 12 in a group. I could also have students 2, 3, 4 in a group, 5, 6, 7 in a group, 8, 9, 10, and 11, 12, 1 in a group. Or I could just have something more random like 1, 5, 6, 2, 10, 11, 3, 4, 8, and then the last group would have to be 7, 9, 12. So I'm understanding a little better now what we mean by the number of ways to form 4 groups of 3 students, and I now think I understand what the problem is asking for. I also get a sense that this seems like a pretty large number. Playing with examples also helps me think about the actual process that I am trying to count. In actually making the groups in my examples, like I did here, I picked the first group, and then I picked the second, then the third, then the fourth. Now, I realize now that that's 4 consecutive choices, and so I'm going to use another concept of problem solving. Is this similar to a problem I've already seen? And it is. Making a sequence of 4 choices is what the multiplicative principle is used for. So I've made a little bit of progress here. I need to find out how many ways there are to form that first group, the number of ways to form the second group, then the third, then the fourth, and then I'm going to multiply all those together. So now the problem is broken down into 4 simpler ones. I would probably not have thought to do this if I had started off just blindly applying formulas to things. I needed to play with the problem first. So let's think about each of these mini problems. So how many ways are there to pick the first group? Well, there are 12 students in all, and I can pick any 3. So again, use the concept, does this look like a problem I have seen before? Well, yes, we've seen problems like this many times, where we select 3 things from a group of 12. If the order doesn't matter, then the answer is 12 choose 3. Otherwise, the answer is the 3 permutation P12-3. So which is it? When I'm forming just a group of students, the order doesn't matter, because I'm not, for example, making one the president, the other the vice president, and the third one the treasurer. So that means there are 12 choose 3 ways to pick the first group. Okay, how many ways are there to pick the second group? Well, this is going to be 9 choose 3 because I'm making a group of 3 from 9 people, not 12 because I've already assigned 3 students. Notice that the picture helps me realize this. Likewise, the number of ways to pick the third group is going to be 6 choose 3, and the number of ways to pick the fourth group is going to be 3 choose 3. Now that last binomial coefficient is 1. Apply another concept. Does that make sense? Well, yeah, that makes sense because in my examples, I noticed that by the time I picked the first 3 groups, there was only 1 choice left for the last one. So by this work, it seems like the answer should be 12 choose 3 times 9 choose 3 times 6 choose 3 times 3 choose 3, and that comes out to 369,600. Now this is fairly believable, but before we declare this to be an official answer, we need to remember to reality check the result. And especially in counting problems, remember we need to scrutinize the work to see if there is any chance that we counted something multiple times that were equal to each other. So playing with more examples helps find the overcounting possibilities. When I do this, play with more examples, I might notice that if I pick 1, 2, 3, then 4, 5, 6, then 7, 8, 9, then 10, 11, 12 as my 4 groups, that's counted as a distinct selection. But if I picked 4, 5, 6, then 7, 8, 9, then 10, 11, 12, then 1, 2, 3, that is also counted as a distinct selection. But this is not any different than the first collection of groups because I'm not putting the groups themselves in any kind of order. So the number I came up with earlier is an overcount. In fact, it overcounts by a factor of 4 factorial, which is the number of ways to rearrange the 4 groups themselves. So my final answer has to take this number and divide by 24, and that gives me 15,400. So this isn't that difficult of a problem in retrospect, but it was pretty difficult at the beginning because it's not the kind of problem that is just a straightforward application of one formula. It was instead a combination of several different concepts, the multiplicative principle, the binomial coefficient, permutations, and we use some general concepts that aren't themselves in any particular formula or method, such as understanding that the initial answer was a fairly serious overcount. What got us through this problem was not the successful application of a formula. It was the successful use of our human brain to play, experiment, observe, and reason, and then pick the right mathematical tools, and then use them correctly. This is a complex set of skills that only human beings have, and you should congratulate yourself on making progress in this direction.